So let's finish off lecture 12 by talking about how polar versus nonpolar molecules can interact with one another in a sample. And so this is what we call non-covalent interactions. These interactions aren't between atoms themselves because it's bonds that hold together atoms to form molecules. We're talking about neighboring molecules. So in a sample of, let's say, water, you'll have a bunch of H2O molecules floating around, to make up the sample. So now the question is, how do the properties, like if it's a polar sample or a nonpolar sample, how do those properties affect how molecules interact with one another? And so these non-covalent interactions are also called intermolecular forces. Inter meaning like between molecules, like international, in between nations. So intermolecular means between separate neighboring molecules. And I'll oftentimes abbreviate intermolecular forces as IMF. And so it's these forces that hold together molecules to form your sample. So if your sample is a solid or a liquid, there are a lot of intermolecular forces holding that sample together, keeping those molecules close to one another. So we can define intermolecular force as the attractive force between molecules. So essentially, in a water sample, how does one water molecule interact with another water molecule? So we'll answer that within these slides. So some points to show is that these intermolecular forces, because they're between molecules, they're a lot weaker than bonds. Remember, bonds are what holds molecules together. All right, they hold those atoms together to form the molecule you want. Intermolecular forces are different. They help us determine what state of matter your sample is at a certain temperature. So if your sample is like a solid or a liquid, there are a lot of forces, intermolecular forces, keeping the sample together while compared to the temperature of the sample itself, because that temperature is actually a disruptive force. Temperature, molecules are moving, and if at a certain temperature there's enough energy there to surpass intermolecular forces, then you won't have a solid sample or a liquid sample. You might have a gaseous sample. So that's what I mean by this last point. Intermolecular forces organize matter either into like a solid sample or a liquid, and we can compare those forces by the motion of the molecules, which is determined by temperature. The higher the temperature, the more disorganized, more disorder, or more energy to overcome intermolecular forces. All right, so some more detail about state of matter when comparing intermolecular forces to temperature. So again, intermolecular forces, if there's a lot of IMF present, then the sample, you can think of those molecules are going to stick together, be a lot more sticky towards one another, and be a solid. So in this first point, if you have a solid sample, that means that the attractive forces from your intermolecular forces are a lot greater than disruptive forces that is defined by your temperature. That you'll have to really up the temperature of your solid sample in order to get it to turn into a liquid or a gas. And you can just like think of ice, water in a solid form, ice at a cold temperature, right? We've lowered the amount of disruptive forces, so the attractive forces of the water molecules can come together, all right, and form your ice block. So we can compare our solid sample, where IMFs are greater than your temperature disruptive forces, to a gas sample. What if it's flipped? What if you have a larger or higher temperature? All right, and there's a lot of energy in your sample. All those molecules are moving around so much that you break the attractive forces holding molecules together. So that's what we mean here, where attractive forces is a lot less is weaker than disruptive forces. So remember temperature, IMFs. So if the temperature is greater, enough to break those attractive forces, your intermolecular forces, those molecules are going to spread out, all right, because you're breaking the attractive forces. They're going to spread out and you'll have a gaseous sample because now the molecules are spread out. They're not attracted towards one another. So you don't have, a defined volume like in a solid or a liquid sample. And then between solid and gas, when the attractive forces from intermolecular forces are somewhat equal to the disruptive forces from temperature, then you'll have a liquid sample. So that's just kind of between. So as you know, as you heat up a sample, like let's say water, as you increase temperature of like a block of ice, you'll have ice. If you increase the temperature of your disruptive forces, right, you'll melt your ice into water, and your ice will become liquid water. And so in that case, the attractive forces are somewhat equal to the temperature disruptive forces. And then finally, if you keep increasing your temperature, right, you put your liquid water sample on the stove, you're essentially adding more disruptive force energy into the sample to overcome attractive forces in your sample, and you'll produce gaseous water or water vapor or steam. Okay, so again, intermolecular forces is a very important concept to understand properties of samples, especially their state. So let's now talk about the different intermolecular forces that we'll discuss in this class. There's 3 different kinds, and we're going to talk about the weakest one first, the weakest force, and then the third one is the strongest of the forces. So the first one we'll talk about is London dispersion forces. This has to do, if you're going to remember one thing, this has to do with temporary dipoles, and it is dependent on molar mass of your sample. The second type of intermolecular force that we're going to learn about are dipole-dipole interactions. And this type of intermolecular force, you need to look for a permanent molecular dipole. Essentially, the molecule must be polar. So again, we're bringing in concepts from that last discussion of molecular polarity. And then the last intermolecular force we're going to talk about is hydrogen bonding, which is just a special type of dipole-dipole interaction, but it just has certain criteria. And this type of intermolecular force is the strongest. And so hydrogen bonding, there needs to be a hydrogen present, connected to or bonded to a very highly electronegative atom. It can be oxygen, fluorine, or nitrogen. We'll talk about that in the coming slides. But these are all 3 that we're going to talk about now. So let's talk about our weakest one first, which is London dispersion forces. So London dispersion forces also are called van der Waals interactions, or sometimes we'll just call it dispersion. All matter, all molecules, all samples have London dispersion forces. It's the weakest force. It has to do with interactions of moving electrons, electron clouds. So my definition for London dispersion force is it's an attractive force because it is an intermolecular force that occurs in all molecules by forming, and I kind of already hinted at it, we're forming temporary dipoles. So I'll explain to you in the next slide what temporary dipoles or instantaneous dipoles mean. So, and I'll show you what a temporary dipole is, but I'll say once one molecule has a temporary dipole, that molecule will induce another temporary dipole in a neighboring molecule. So remember our dipole arrows, right? There's a positive side and a negative side. And so you can kind of think of them like magnets. And so if there's an instantaneous dipole, a temporary one that only exists for like a fraction of a second, That dipole exists, so it will induce another temporary dipole in another molecule. Yeah, and so it only lasts for fractions of a second. All matter has London dispersion forces, but it is most important in nonpolar compounds. So London dispersion is the most important. It's the most dominant intermolecular force in nonpolar compounds, because we will see in the next, as we complete this talk, is that nonpolar compounds cannot participate in the other two intermolecular forces that we are going to talk about. So London dispersion, super important with nonpolar compounds. And the big thing that I want you to get at is that London dispersion, that force increases as molar mass of your compound increases. And I'll show you an example in the next slide. So let me explain to you what I mean by temporary dipole. All right, so I have an example here. So I have a hydrogen sample, so diatomic hydrogen, H2 gas. If I asked you to write the Lewis structure for hydrogen gas, you would write this, right? Hydrogen bonded to another hydrogen, and count your valence electrons. It's all good. So there's your Lewis structure. So remember that this bond contains 2 electrons in it. So I could also write it like this, where these 2 dots represent that bond between hydrogens. So Lewis structures aren't, they're just one way for us to represent molecules. But the problem with Lewis structures is, as you look at this, it looks like these electrons holding together these hydrogen atoms are stationary, but they're not. They're not stationary. Remember our definition of atoms, that we, have a nucleus in the center, and then we have this extranuclear region where the electron can be anywhere within that extranuclear region, that the electron isn't just stationary, it's actually moving around. So when we bring 2 hydrogen atoms together, we're combining those extranuclear regions of the 2 hydrogen atoms. So essentially, instead of those 2 electrons being stationary, those 2 electrons are now able to move around in either hydrogen's extranuclear region. So they're actually moving around. And that's what this picture is showing, that this circle is showing the extranuclear region around the molecule, that the electrons in hydrogen can be anywhere within this oval. Okay, so now that you know that electrons can move around, let's say, okay, so there's 2 electrons in here somewhere. Let's say we take a snapshot in time, all right? And maybe in that fraction of a second where we took that snapshot, 2 of the electrons are closer to one of the hydrogens, let's say the left hydrogen, more so than the right hydrogen. So both of the hydrogens are on this side of the molecule, just for a split second. We just take a snapshot in time. So this is what we call an instantaneous or temporary dipole. It only happens for a split second because, once that I take the picture and it's over, the electrons are going to move around. They'll just keep moving around. But just in that fraction of a second, that snapshot, those 2 electrons are on this side of the molecule. So now you see we have this kind of uneven distribution of electrons. And this picture, now we can draw a dipole arrow to represent this, because 2 of the electrons are more towards the left side of the molecule and not on the right side. So we could say that the left side is slightly negative, leaving the other side slightly positive. And that's the picture I have down here. All right. So if more of the electrons, in an instance are more on the left side, we create this dipole. Temporary. It only exists for a split second. So if this exists for a split second, we have this dipole arrow. You can think of them as these dipole arrows as magnets. Now this end of the hydrogen molecule is slightly positive. So if there's a neighboring molecule, so molecule B, this is another hydrogen molecule in our sample. Remember, electrons are negatively charged, right? So if this side of the molecule is positive, this electron, or even both electrons, are going to slightly be attracted towards this side of of the molecule, creating its own temporary dipole. So that's what I mean by one temporary or instantaneous dipole induces another instantaneous dipole in another molecule. All right, and so you can see that, if I draw the two dipole arrows, you'll see, that the negative side of this molecule is attracted towards this positive side of the other molecule, and it's this interaction. This is what we call London dispersion force. So there is our attractive IMF force, where we have two instantaneous dipoles being attracted towards one another, that the positive end of one molecule is attracted towards the negative end of another molecule. But again, after we take that picture, then those dipoles go away. They only exist for a fraction of a second, but then maybe, in the next second, that a temporary dipole will form again. All right? So that's what I mean by London dispersion forces. But really what I want you to get at, what the most important thing, is that London dispersion forces, that attraction, so this, the attraction between the positive and negative sides of the temporary dipole, that attraction will increase when your molar mass of your sample increases. So that is probably the most important thing. And the reason for that is as molar mass increases, this increases the number of electrons in your sample. So if there are more electrons in your sample, there are more chances that you can make instantaneous dipoles. So that's the reason why we see this trend, that London dispersion forces increase as molar mass increase. And the important thing is that this type of force is very important for I guess I should say that non-polar substances only have London dispersion forces. So this type of force is very important to understand with non-polar substances. So I'll give you an example. So I'll give you a series of samples. So let's look at diatomic chlorine, diatomic bromine, and diatomic iodine. All of these samples are nonpolar because it just like diatomic hydrogen, it's nonpolar. If you calculate difference in electronegativity, it's 0. All right, these essentially all look the same. They're linear, right? So if you look on the periodic table, I just picked the halogens going down. So going down, chlorine, bromine to iodine, our molar mass increases, going from chlorine, bromine to iodine. So we would also predict that our London dispersion forces increases, right? Okay, so what does that mean? What do we see when we see these samples? So again, London dispersion force is just an intermolecular force. If the attraction increases, right, it means that iodine, because it has the most attraction, the most London dispersion forces, that the stickiness holding together the molecules is quite strong. That diatomic iodine is the stickiest. So that means it's going to require a lot more energy. We have to raise the temperature a lot in order to make it a gas, in order to overcome the intermolecular forces holding together that sample. And what's really interesting with these 3 different samples at room temperature, so that's like 20 degrees Celsius. At room temperature, diatomic chlorine is a gas. Bromine, if you had a bottle of bromine Br2, it's actually a liquid. And then iodine, I2, is actually a solid. So what you're actually seeing, because molar masses increases in this series, London dispersion forces increase. And what also increases is your boiling and your melting point increases. So if your boiling point, the amount of energy or temperature you need to make a solid turn into a liquid to a gas, or sorry, yeah, liquid to a gas increases. You're going to have to put a lot more energy to make it a gas. And so that's why diatomic iodine is a solid at room temperature, because it is the stickiest. It has the most London dispersion forces. There's a lot of attraction keeping those molecules together. Compared to chlorine, diatomic chlorine, it has a lot less London dispersion forces holding it together. So even at room temperature, that is enough energy to make it turn into a gas. So that series is a really great way to represent the how London dispersion forces translates into properties, in this case, melting point and boiling point of these three different halogens. Okay, so, and then remember, London dispersion forces comes from temporary dipoles. That attraction increases when molar mass increases. All right, so we've talked about these nonpolar substances. So what about polar substances? That comes to our second intermolecular force, dipole-dipole interactions, right, on our list. So, so let's just get through the definition. So this type of interaction will happen only between polar molecules, where the partially positive end is attracted to the partially positive end is attracted to the partially negative end of another molecule. So that's a super important part of this definition of another molecule, because this dipole-dipole interaction is between different molecules of the same sample. Like if we talk about water, it's how one water molecule is interacting with a dipole of another water molecule. So dipole-dipole is kind of similar to our previous, my explanation here, kind of the last slide of our London dispersion, where we have, the positive end of one molecule interacting with the negative end of another molecule. The only difference here is that in London dispersion, these dipoles are temporary. But in our dipole-dipole interaction, we are talking about molecules that have permanent dipoles or polar molecules. That's what I mean when I say permanent dipoles, because I have to contrast that with temporary dipoles from London dispersion. All right. Okay, yeah, so this is the interaction between permanent dipoles and a polar molecule, and it can only occur in polar molecules. But remember, polar molecules will also have London dispersion. It's just not as important because the dipole-dipole interaction is stronger. Okay, so let's look at an example. We have a molecule here, fluorine monochloride. All right, so if we draw the Lewis structure of fluorine monochloride, and there's some lone pairs there. All right, so this is a polar molecule. If you look up the electronegativity chart for these atoms, fluorine is like 4.0, and I think chlorine is 3.5. All right, so that means fluorine is more electronegative. So I think that's what I have there. Yep. So fluorine is more electronegative. So we can draw our partial negative sign on fluorine and partial positive on chlorine. So this is what I mean by there's a permanent dipole there. That this dipole doesn't go away because we drew it because of where the atoms are in this molecule. So what I'm saying is that this permanent dipole can interact with another permanent dipole on a neighboring molecule. So if this chlorine end is positive, it's going to be attracted towards a partially negative end. I'll just draw it like weird like this. A partial negative end of another fluorine monochloride molecule. All right, and so you can see how that positive negative ends, they're being attracted towards one another. And that's the stickiness that we're talking about, that attraction is a force that needs to be overcome in order to separate your molecules to turn into a gas. All right, so here is a fluorine monochloride sample. It's an ensemble of a bunch of these molecules. So you can see, again, we have it shouldn't be whole negative charges. It should be partial, right? Partial negative, partial positive, partial positive, partial negative, right? In this picture, you see that we have a bunch of interactions where the slightly positive chlorine part of the molecule is attracted towards the negative part of a neighboring fluorine. And then again, all these arrows that you see, this is our dipole attraction. So I'm not sure if this sample is a solid or a liquid or something, but in order to make this sample a gas, we have to break all of these attractions, all of these, sticky magnets trying to stay together as like a liquid or solid sample. In order to make it a gas, we got to break those in order to get it apart. All right, and so that's what we mean by intermolecular force. In this case, it's a dipole-dipole interaction between permanent dipoles of this particular molecule, fluorine monochloride, where those permanent dipoles, you can even draw them on all the molecules, are interacting with one another, where the positive and negative ends are more attracted towards one another. Okay, so I think next we're going to talk about the relative strengths of dipole-dipole interactions. So remember I told you with London dispersion that intermolecular force increases with molar mass. Dipole-dipole is different, so it has a different trend. But the first thing I want to note is that dipole-dipole, this interaction is stronger than London dispersion, although we are still talking about how, those dipole arrows are being attracted towards one another. Because dipole-dipole involves permanent dipoles of polar molecules, London dispersion involves only temporary dipoles. That dipole-dipole will be the stronger of the two, because the London dispersion, those dipoles only exist for, a fraction of a second. All right. So then finally, so the strength of dipole-dipole interactions, that trend depends on how big your dipole arrow is, how big your permanent dipole arrow is on your molecule. So the strength of dipole-dipole will increase with increasing size of your permanent dipole, which essentially just translates into the electronegativity difference of the two atoms that you're looking at. So here's an example. So our fluorine monochloride example. Oh, did I get that wrong? Whoops. So it should be 3.0. Is that right? Okay. 3.0. All right. So we have three different molecules: fluorine monochloride, fluorine monobromide, and fluorine monoiodide. So all of these kind of have the same structure, right? It's a fluorine bonded to a chlorine, fluorine bonded to a bromine, fluorine bonded to an iodine. Right? So these are all polar molecules. You can write electronegativities for all those atoms, but what we're going to look at is the electronegativity difference between the two atoms. So if you look those up on the chart, your delta or your difference in electronegativities of fluorine monochloride is 1. Between fluorine and bromide, it's 1.2, and fluorine and iodine, it's 1.5. So because the electronegativity difference is smallest for fluorine monochloride, that molecule will have the weakest dipole-dipole force. So essentially, you can think that the dipole arrow for fluorine monochloride is smaller, while fluorine monobromide will be a little bit bigger. I'm just going to exaggerate it. Right, it'll be a little bit bigger because our difference is slightly bigger. It's 1 to 1.2. And then finally, fluorine monoiodide will have the biggest dipole arrow because it has the largest electronegativity difference between the two atoms. So that's the trend that you will see as your dipole-dipole interaction or attraction increases as your electronegativity difference increases. So if we had to predict boiling points here, fluorine monoiodide would have the highest boiling point, while fluorine monochloride would have the lowest boiling point. And how I figured that out is that fluorine monoiodide, because it has the strongest dipole-dipole interaction, it is the stickiest, right? That the molecules are being attracted towards one another the most. So it's going to be really sticky, and so it's going to take a lot of energy to separate those molecules to turn it into a gas. So that's why I say that Fi will have the highest boiling point, while FCl, because it has the weakest dipole-dipole interaction, will have the lowest boiling point of this series of three. Okay, so let's talk about our last intermolecular force, which is hydrogen bonding. Hydrogen bonding is our third and strongest intermolecular force that we will talk about in this class. So hydrogen bonding is just a special type of dipole-dipole interaction, but it has a couple criteria. The interaction needs to be between a hydrogen atom and a highly electronegative atom. That's what I have here. Has to be, obviously a hydrogen has to be involved because we're making hydrogen bonds, and a highly electronegative atom, which for us will be fluorine, oxygen, or nitrogen. So let me go into the details of the requirements you need for a hydrogen bond to occur. So you need to have a hydrogen, the hydrogen bond. Then the second criteria is the electronegative atom. You need to have a fluorine, oxygen, or nitrogen in the chemical formula. So that's kind of what you need to look for in a molecule in order to see if hydrogen bonding can occur. The third requirement is that hydrogen needs to be directly bonded to that fluorine, oxygen, or nitrogen that's in the formula. So it needs to be directly bonded to it. And then finally, there has to be at least one lone pair on that fluorine, oxygen, or nitrogen. All right? And so essentially what you're looking for in a molecule is there a part of the molecule that looks like this: a hydrogen bonded to a fluorine with at least one lone pair on it. Or you can look for a hydrogen connected to an oxygen with one lone pair on it. Right, and other stuff can be there. It doesn't matter. But, it's this structure is what you're looking for. And then finally, a hydrogen with a nitrogen bonded to it and at least one lone pair. So how this interaction happens, it's similar to dipole-dipole in that the positive end of one molecule is attracted toward the negative end of another molecule. In hydrogen bonding, the hydrogen itself on this part of the molecule is very electropositive. So in all of these pictures, essentially all the electron density is on this electronegative atom, leaving the hydrogen very electropositive. And then like fluorine, oxygen, and nitrogen are very electronegative. So there is a very strong dipole here that you can draw on all of them. Hydrogen, the positive part of our dipole arrows on hydrogen, pointing towards the electronegative atom. So you can see how this is exactly the same as dipole-dipole interactions. It just involves these specific cases. And so what you'll see in a dipole-dipole interaction, so if we think about like hydrogen and nitrogen, right? There's a lone pair on nitrogen. So this is, one part of a molecule. What's going to happen is that a hydrogen and nitrogen part of another molecule, that hydrogen is going to be attracted towards the negative part of, the nitrogen part of this particular molecule, while hydrogen is slightly positive. So again, this is just another special type of dipole-dipole interaction where the negative end is attracted towards the positive end. And then, of course, you can keep going, like if another neighboring molecule, hydrogen, nitrogen, all right, there's another interaction that you can draw there. Right? So this, again, is just a special case of dipole-dipole interactions when you have to look for these specific features on your molecule. And so one of the best examples for hydrogen bonding is actually water, liquid water. All right, so water has the chemical formula H2O. And so if we actually draw its Lewis structure for H2O, we have oxygen as our central atom. We have 2 hydrogen bonds, and if you count your valence electrons, you'll see that you need 2 lone pairs on oxygen. So if we look back at our rules for hydrogen bonding, right, you need to have a hydrogen. There's a hydrogen. You need to have an oxygen, fluorine or nitrogen. We have an oxygen. It has to be directly bonded, which it is, and then we need to have 1 lone pair on your electronegative atom, which we do. We have one here. Or again, if you're just looking for these specific cases, so we have that in water. We don't only just have 1 case of hydrogen bonding, we actually have 2. And that's what makes water special, is that we can hydrogen bond on this side of the molecule and on this side of the molecule. All right, so there's 2 places that hydrogen bonding can occur. And so this liquid water sample is an example of how water can hydrogen bond in a liquid sample. So you can see here, so here's a water molecule. The red circle is oxygen, and then the little blue circles are hydrogen. So you can see in all of these cases is that the hydrogen is being attracted towards the partially negative side of the oxygen, or sorry, the water molecule, which is where the lone pairs are. Let me do a different color. It's essentially where the lone pairs are on that oxygen, because hydrogen is slightly electropositive. So it's going to be attracted towards those lone pairs. And so you can see in all of these dotted lines, that's the hydrogen bond interaction that we're talking about. So that's your hydrogen bond. And there's a bunch of them here. And you can kind of see, because of the structure of water, you can kind of see these hexagons start to form. And that's a reason why snowflakes look the way they do, because water can form these ordered structures, at least, in the solid state. And that's a consequence of the strong hydrogen bonding that water has that property. And so that's why we see snowflakes the way they are. Because of that ordering from hydrogen bonding. Okay, so let's summarize all 3 of our intermolecular forces that we have talked about. So our weakest intermolecular force, the first one we talked about, is London dispersion. So I'll just remind you that London dispersion, the extent of that intermolecular force, is based upon molar mass of your compound. The next strongest force is dipole-dipole. Dipole-dipole. And so in dipole-dipole, you need to have a permanent, I can never spell it right, permanent dipole. So meaning you need a polar molecule. It has to be polar. Polar molecule. And then our strongest intermolecular force, the one we just talked about, is hydrogen bonding. And again, hydrogen bonding is just a special case of dipole-dipole, but essentially you just need a hydrogen-oxygen bond, or you need a hydrogen-nitrogen bond, or you need a hydrogen-fluorine bond in your molecule. And then, this type of interaction that we talked about up here, where the lone pair interacts with the electropositive hydrogen. So you need that in order to have hydrogen bonding. That's what you're looking for. All right? And then again, so just kind of to summarize, the more IMFs present, the more the molecules will stick together, meaning that your boiling point will typically increase. So actually, I'm just going to write it like this. So if IMF increases, so generally, like if it's London dispersion or dipole-dipole or hydrogen bonding, if your IMF increases, typically what you'll see is your boiling point will increase. Okay, and so because of that, polar molecules, because polar molecules will have dipole-dipole or perhaps hydrogen bonding, those molecules tend to be liquids or solids at room temperature. Because they stick together more, you need more energy to separate those molecules to become a gas. And then nonpolar molecules tend to be gases at room temperature because the only intermolecular force there is London dispersion, and that's fairly weak. So it's very easy to break apart those London dispersion attractions with a low amount of temperature energy. Right? And again, so when to get those molecules to separate or essentially turn it into a gas, you need to increase your kinetic energy or essentially your temperature of your sample in order to break those intermolecular forces to turn your sample into a gas. All right, so that kind of just summarizes all intermolecular forces that we'll talk about in this class. So let's kind of just review with a learning check. So let's identify the major or dominant type of attractive force in each of these substances. So when I mean major, so like let's look back at the strength. Everything will have London dispersion, and it's the weakest. So if you have a sample that has London dispersion and dipole-dipole, it's always the strongest interaction that will be the most dominant. So if I have a sample that has London dispersion, dipole-dipole, and hydrogen bonding, its hydrogen bonding will be the most dominant intermolecular force. Okay, so with this learning check, we are combining everything we learned in lectures 11 and 12. We need to know the Lewis structure of the compound. We need to know the molecular shape. We need to know whether the molecule is polar or nonpolar. That's the important thing. Polar versus nonpolar. And then finally, we need to apply our rules for intermolecular forces. So that's what we're going to do here. So I'm not going to go into the major details of Lewis structures for this first one. So I'll just write it. So nitrogen trichloride. Okay, this is the Lewis structure where there is a lone pair on the nitrogen. And so this has a trigonal pyramid shape, pyramidal. All right, and the electron geometry is tetrahedral, where that lone pair is like the top site of the tetrahedral. So this molecule is polar because there's a lone pair here that's kind of disrupting the symmetry. So this is a polar molecule. All the sites around nitrogen aren't the same. So those bond dipoles aren't going to cancel out. Great, so it's polar. So that means that dipole-dipole is one of the forces there. And of course, London dispersion is there, but it's the weakest. Everything has London dispersion. Then the last thing we need to check, does it have hydrogen bonding? Well, NCl3 has no hydrogen, so hydrogen bonding can't occur. So this molecule has both London dispersion and dipole-dipole, but its dipole-dipole is going to be our dominant force because it's the strongest. Okay, so there's that example. So let's do water now. So water has this Lewis structure. It also has a tetrahedral electron geometry, but it has a bent molecular geometry. And kind of like in our previous example, because of the existence of those lone pairs that's disrupting our symmetry of our tetrahedral, this also has a permanent dipole. So this is also polar. Water is polar. That's why it's such a great solvent. So it's kind of the same steps. This molecule has London dispersion because everything does. It also has dipole-dipole because it's polar. But then the last thing is it also has hydrogen bonding. It's capable of hydrogen bonding because we have a hydrogen attached to an oxygen that has at least one lone pair. So this can also hydrogen bond. And we already talked about water hydrogen bonding. So to identify the major or dominant force, it's always the strongest one. So in this case, hydrogen bonding is our dominant. Okay, let's keep going. So diatomic bromine. So bromine looks like this. It's Lewis structure, some lone pairs. It's linear. But if we calculate its bond dipole, it equals 0. So it is a pure covalent compound. So this is a nonpolar compound. We already talked about it being nonpolar. All right. So the only, and I'll say it's linear, the only intermolecular force possible for this compound is London dispersion. It can't do dipole-dipole because there's no permanent dipole. It can't do hydrogen bonding because there's no hydrogens. So London dispersion is our dominant intermolecular force present in diatomic bromine. Okay, what's next? KCl. So KCl is ionic. So K and a Cl, it's an ionic bond. All right, well, I want to draw it like that. All right, it's a cation and an anion. And so if you look up the bond electronegativities of these two molecules, or sorry, these two atoms, if you look that up, let me just quick look it up. Here, okay. Where's potassium? Potassium is 0.8 and chloride is 3.0. All right, so 0.8, 3.0. So those are our electronegativities. So if we drew our bond dipole arrow, it would look something like this. Okay, it's an ionic bond. It is definitely polarized. And so this would be a very polar molecule because it has an ionic bond there. And so if we look at our intermolecular forces, the first one we talk about is London dispersion. Yeah, it has London dispersion. It also has dipole-dipole because it's polar. And then our last one, hydrogen bonding, there are no hydrogens. So, whoops, that's a Cl, sorry. So here, dipole-dipole is our dominant force. Okay, hopefully you're getting the hang of this now. So the last one is NH3. So I'll draw that Lewis structure, and it's a similar structure to our NCl3 example. So this is ammonia. So just like in our nitrogen trichloride example, this is also trigonal pyramidal shape. Right, so that lone pair is disrupting our symmetry, so this is a polar molecule. That more of the electron density will reside on near this lone pair than opposed to the other side of this molecule, so there's an overall bond dipole or molecular dipole pointing towards the lone pair. It is polar. So if we go through all of our intermolecular forces, okay, it has LDF. It also has dipole-dipole because it's polar. Now the last example, hydrogen bonding. So let's remember the rules for hydrogen bonding. There has to be a hydrogen. There are hydrogens. And look, these hydrogens are connected to an electronegative atom, nitrogen. Nitrogen was one of our examples. And look, there's a lone pair. So ammonia can undergo hydrogen bonding. Right? Let me just show you. Remember, these are the types of bonds, structures that we're looking for on our molecule. So you see that ammonia has this structure on it. Okay, so we have all three of our intermolecular forces. So ammonia's most dominant intermolecular force is hydrogen bonding because it is the strongest intermolecular force that we have learned about. All right, so here are all my answers to this. This type of learning check, being able to identify intermolecular forces, really is comprehensive in that it kind of forces you to know how to do Lewis structures, how to do molecular shape, how to understand molecular polarity, and finally apply intermolecular forces. So really the last two chapters have really built upon one another. So if you're having trouble with one of these 4 steps, definitely review those parts of lectures 11 and 12 before moving on. So in the next lecture, we're going to talk about chemical reactions. See you then.